My name is Zaira. I'm going to brief the part of the 2.2, and this is the block diagram for the simulation 2.2. The step for the 2.2, we need to set our value for the P. So because this is a try and error for the P controller, so our P is 0.3. And then we'll get this graph. The yellow one is the ref and the blue one is the speed. So for we can check the rise time and overshoot here in the box at the right side.
It's not Mira Natasha Mtizaro. My metric number is CE 2054, and I will explain about 2.3 experiment using PI controller. As you can see, this is the block diagram. And as you can see, this is PID controller at here. At here, we can change the type of controller and we choose proportional integral. After we run in the graph in beginning, we can see the output is more than input. So we indicate that we need to modify the value of parameter, which in here and also in here, we change to 0.03 and 0.001. And after that, we get the result.
My name is Zaira. So the next is 2.4, which is experiment using PD controller. The circuit is still the same as our previous for 2.2 and 2.3, but the difference we just need to change the PID controller into PD. So here still try and error method. Our value for P and D is 0.03 and 0.01. So after we double click the PD controller and we set the values as I said before. So this is the output. Then you can check at the scope. The yellow one is for the reference while the blue is for the speed. Then we can check our value for overshoot and rise time at the table on the right side.
2.5 experiment using PID controller. The block diagram PID also the same thing. We choose the controller PID in the parameter block. And after run, we modified the value at P, I also the derivative value. And we choose the PID controller. After we run and we get the result, it's the output is below than input.
Assalamualaikum and hi, my name is Muhammad Azwari bin Zulkifli. So today I will continue part 2.6. Summarize our result in a suitable table. Okay, so we list out the controller P, PI, PD and PID. So this is the value of rise time in millisecond. 230 for P, 306 for PI and 771 for PD and 828 for PID. So we can see the value of R is increased, and then for the maximum overshoot and the value of maximum overshoot is decreased for P 12.93 and for PI 6.989 and PD 0.502 and PID negative 0.344. Okay, this is the steady state response compared to the set desired value is 3000. So to get the steady state error, desired value multiply minus which actual value. So we can see that the steady state error for P and PD is higher, and then for PI and PID is close to the desired output.
Assalamualaikum and hi, my name is Izzah Hazira binti Hijir and my metric number is CE190220. 2.7 Discuss and compare all the results above with the expected effects. So I will compare to the expected result from all our graph we saw to graph and less stable compared to the graph we obtained from before at 1.4 the perimeter. The feedback loop in 1.4 not really stabilized compared to the graph we obtained. So the increasing the response time and robust time or reducing them change the output of the tune graph, but the steady state still ends at 2933, which means the system stabilized at the time, which is same time with the time response. So that's all from me. Thank you.
My name is Zaira. I'm going to brief the 4.2 simulation. So for this part, it's using the P controller by using auto tuning method. So the first step for the auto tuning method, we need to check our value of P. So for our group, we did 0.03. Next, after we click the auto tuning at the piece parameter, this setting of the auto tuning will open, and we need to adjust the response time, and then we need to update the block. Then we'll get this new output of the block diagram for P controller. You can check the block of the P controller to see the new value for P, which is here is negative 0.28. Then lastly, this is the output of the block diagram. We can check this graph on the scope after we run the whole simulation.
I will explain about 4.3 experiment using PI controller using auto tuning method. This is the block diagram. It's same with before, but the difference in the parameter blocks. At here, as you can see, I was circled it at tune with this experiment using auto tuning. So this method need to select the tune, and after that, it's with auto tuning, and this is the result after auto tuning. He will give the best result of professional. Also the value adjust at response time and transit behavior. After that, this is the value that we get of the auto tuning. It's become changed than before. After that, this is the result of the graph. The output is below than info.
Okay, Assalamualaikum. My name is Muhammad Zuhairi bin Zulkifli. So today I will continue part 4.4. Just I need to do auto tune for PD. So firstly we click the PID controller, and then we set to the PD and click apply and click auto tune and wait for it. So this is the graph response for PD after tune. So we click update block and then we close. So this is the value of P after tune and also D and filter coefficient, and then we click run and we click the scope. So this is the ground response, which is higher from the very higher from the desired output. Also the steady state error is very higher. Okay, next for 4.5 we need to do auto tune for PID. So we click this PID controller, and for the controller we set to the PID and then we click apply. So this is the try and error value. So we click auto tune and wait for it. So this is the ground response for PID after tune, and then we click update block, then we close, then we click run, and then we click the scope. So this is the graph response for PID controller, and this is the steady state response, and we can see the rise time and also the overshoot.
Assalamualaikum and hi, my name is Iza Hazira binti Hikzir and my matric number is CE190220. So regarding for the part 4, and I will explain about 4.6, summarize of the result in a suitable table. So this is a table which is contain about controller P, PI, PD and PID, and also contain which is a rest time in milliseconds, maximum overshoot, steady state response and steady state error. So for the controller type P, for the rest time is 11.102 milliseconds, and for the maximum overshoot is 0.505. For the steady state response is 2005, and last for the steady state error is 995. For the controller type PI, that we've got for the rest time is 476.107 milliseconds. And for the maximum overshoot is negative 0.200. For the steady state response is 2804, and for the steady state error is also same with a steady state response. So for the controller type PD, for the rest time is 0, and for the maximum overshoot is also 0. For the steady state response is 1412, and for the steady state error that we've got is 14,540. So lastly, for the controller type PID is 508.482 milliseconds. For the maximum overshoot is 13.068. For the steady state response is 3091, and lastly for the steady state error is also same with the steady state response, which is 391. So we move to the next slide, and which is the point for 4.7. Discuss and compare all the results above with the expected effect in a section 1.4. So all the result is compared to the expected result from all our graph saw a graph and less stable compared to the graph we obtained from the before at 1.4, which is the parameter. The feedback loop in 1.4 is not really stabilized compared to the graph we obtained in here. So the increasing the response time and the raw boost time or reducing them change the output of the tune graph, but the steady state still ends at 3091. So which means the system is stabilized at the time response. So that's all from us. Thank you.